Hello viewers and a warm welcome to my YouTube channel. Today we are going to see the second lecture in sequences. Last week I had uploaded the first lecture video on sequences. This is what we had gone through. So we began with the definition of sequences. We saw a few examples on sequences and then we talked about the important topic on limit and convergence of a sequence, and for which we had seen a couple of examples. There was also a question which was put over to you. Today, we are going to start with the topic about uniqueness of limits. So, the uniqueness of limits can be discussed with the help of a theorem, and it simply says that a sequence can have at most one limit. So, let us start with the statement. Suppose we talk about a sequence xn, and it is a convergent sequence. Then x will have exactly one limit. Now we prove this with indirect method, and we will say that suppose the sequence x, which is convergent, has two limits. We will say let x have two limits, say a and b. Now our task will be to show that a and b are going to be equal. Now, once we say that sequence has two limits a and b, we can apply the epsilon n naught definition for the limit a as well as the limit b, and we get that for any epsilon positive, we can find out a natural number n1 such that the distance between xn and a can be made lesser than epsilon by 2 for all natural numbers n greater than or equal to 1, and also there exists another natural n2 for the same epsilon such that the distance between xn and b can be made lesser than epsilon by 2 for all n greater than equal to 10. Now you might be wondering that we have taken epsilon by 2 instead of epsilon. We will understand that in due course of time. It is a kind of an adjustment factor which we have kept instead of taking epsilon for the convenience to prove the result. Let me choose a natural number n0. We choose n0, which is going to be taken as maximum of n1 as well as n2. Then for n greater than equal to n0, we can get into action the inequalities from equation 1 and equation 2, and let us talk about the difference between a and b. Now since we are interested in utilizing equation number 1 and equation number 2, if you will see that a is associated with xn and so is b, so we are going to add and subtract here an adjustment factor of xn. So let's say a minus b plus xn minus xn. Now we can bring these two together, the one with the minus sign, and we can take b along with xn. So this can be rewritten as minus of xn minus a and plus xn minus b. So now you might be understanding why we have added and subtracted xn. Now we will take help of the triangle inequality. The triangle inequality says that if you are having two real numbers x and y, then mod of x plus y is always lesser than or equal to mod of x plus mod of y. Now instead of x we have xn minus of xn minus a, and instead of y we have xn minus b. So applying the triangle inequality, this can be rewritten as mod of xn mod of negative xn minus a plus mod of xn minus. Further, we know that mod of x is same as mod of minus x, so that we can apply to the first modulus. So this is going to be mod of xn minus a and mod of xn minus b. Now since we have said that n is greater than or equal to n0 and n0 is the maximum of n1 and n2. So to understand this, let me just have a number line over here. So let's say this is the number line, and let me place n1 and n2. Without any loss of generality, let me say that n1 is smaller than n2. So we will have n1 to be somewhere placed over here, and since n2 is bigger, it will be placed on the right. Now clearly, if I choose n0, which is the maximum of n1 and n2, then this is going to be n. So your n2 is same as n0. Now look at the inequality in 1. It is applicable for all natural numbers which are bigger than n1. So it is applicable on this part for all the natural numbers on the right of n1. And same if you will look at inequality number 2, so that is applicable for all natural numbers which are bigger than n2. Now we need a common range. So since we have chosen n0, we can see that both the inequalities are actually applicable for n equal to n0. So thus we can say that mod of xn minus a is lesser than epsilon by 2, and so is mod of xn minus b. So thus we started with on the left as mod of a minus b. We are going to get this to be lesser than epsilon by 2 plus epsilon by 2, which is epsilon. And over here your epsilon is arbitrary positive real number. So thus we are having that mod of a minus b is lesser than any positive real number, and this is only true when mod of a minus b itself will be 0. So thus we get that a minus b is 0, and finally we can write on the conclusion saying that a is equal to in the beginning we stated that the sequence has two limits, but towards the end of the proof we have got that the limits are going to be same, and thus we can conclude that therefore a sequence x, if convergent, can have exactly one. Now moving ahead, we will talk about various equivalent forms of the epsilon n0 definition of sequences. So from the epsilon n0 definition, we know that a sequence x converges to a real number x if and only if for any positive epsilon we are able to find out a natural number n0 such that the distance between xn and x can be made lesser than positive epsilon for every n greater than equal to n0. Now here we are going to take help of some modulus property, and using that we will be writing down more variants of the convergences of sequences. So let me put up this as 1, and we are going to write down various equivalent forms of this. So the expression on the left of this we can be also written as minus epsilon is less than xn minus x is less than plus epsilon, which is same as x minus epsilon less than xn less than epsilon plus x. This is nothing but the definitions of open neighborhoods. So we can say that xn belongs to the neighborhood centered at x with radius epsilon. So we can also say that the sequence x converges to x if and only if for any positive epsilon we can find a natural number n0 such that xn belongs to the neighborhood centered at x and radius epsilon for all natural numbers n greater than equal to n. Let us just see one example and try to utilize the second definition which we have stated, which is this one, where we are taking help of the neighborhoods. Let me consider a sequence x which is given by say 0, 1, 0, 1, 0, 1, 0, 1 and so on. So it will not be difficult for you to write down the formula wise notation of the sequence. So we can say that the sequence x has term xn where xn takes only two values, one is 0 and one is 1. Now if you will see that the sequence x has zeros at the first position, third position, fifth position, that is when n is odd, and while n is even, the sequence has 1. Now we are going to talk about the convergence of this sequence. So suppose you make a claim that the sequence x converges to 1. So if we were to apply the definition over here says that for any epsilon positive, you should be able to produce a natural number n naught such that all terms of the sequence after this natural number n naught are going to be contained in this neighborhood. So let me draw a number line first. So here we have the number line and let me place up the limit. So this is the limit which we are saying 1. Now since the above statement is true for any positive epsilon, so let me here take epsilon as 0.5. Now for this epsilon 0.5, you should be able to produce a natural number which is going to push all the terms of the sequences in the neighborhood centered at 1 with radius epsilon. So let us first draw the neighborhood at 1 with radius epsilon. So this is going to be an open interval from 1 minus 0.5 up to 1 plus 0.5, and that is going to be 0.5 up to 1.5. So over here geometrically it is easier to understand that this is the center 1. Now we are taking radius as 0.5. So on the right we are going to move 0.5 units and come up to 1.5, and on the left also we are going to move 0.5 units. So we'll have to move 0.5 units on the left. So this is going to be 0.5. So this is the neighborhood which we are currently talking about. And this is an open neighborhood, so the boundaries are not included, which you can see from the parenthesis over here. Now let me take n naught equal to 6. Since 6 is an even number, the sixth term is 1, which is very well inside the neighborhood. So you can see that x6 equal to 1 is contained in the neighborhood centered at 1 with radius 0.5, and we are choosing n naught equal to 6. Now what happens when you take the next term? So the next term is x7. So the x7, since n equal to 7 is an odd number, and by the definition the sequence value is going to be 0. Now this 0 is not contained in this neighborhood. So it is violating the definition that for after this term onwards, all the terms of the sequence should be present in this neighborhood, in this yellow highlighted patch. But we can see that x6 is going inside the neighborhood and x7 comes out, and then again x8 will go inside the neighborhood but x9 will come out. So it is not applicable for all terms of the sequence after 6. So thus n naught equal to 6 doesn't work. And for similar arguments you can say that any n naught which is an even number will not be helping us to test the definition. Now what will happen if someone takes n naught as an odd number? So let me take n naught as 9. So if I take n naught as 9, and since it is odd, so your x9 is going to be 0, and clearly 0 is not contained in your neighborhood. So we know that n naught equal to 9 will not work, but x10 again it is an even number and it will lead us back to this case where we have taken n naught equal to 6. So thus we are having violations in both the cases, and so our assumption that x converges to 1, it is not going to hold. And on similar arguments you can also show that suppose x converges to 0, this particular argument is not going to hold. Later on it can also be shown that the sequence in example 7 is not convergent, as you can see that the sequence terms are oscillating between two values 0 and 1. So it does not move towards a specific value for higher and higher values of n. Next we are going to talk about the tail of a sequence. So we give the definition for m tail of a sequence. To begin with, start with the sequence x equal to xn, and let's say this is equal to x1, x2, x3. There will be some natural number which will be giving us the term xm, followed by xm plus 1, xm plus 2, and so on. The m tail of this sequence is a sequence given by xm, and this is going to be starting right from m plus 1. So we'll have xm plus 1, xm plus 2, xm plus 3 and it goes indefinite. Let us see a quick example for the same. So if I define sequence x as say xn and I put up the rule for xn as n cube plus 1. So let us first work out with the initial terms of the sequence. So you can see that x1 is going to be 1 cube plus 1, which is 2. x2, it is 2 cube plus 1, which is 9. x3 is 3 cube plus 1, which is 28. x4 is 4 cube plus 1, which is 65. And x5, which is 5 cube plus 1, which is 126. Of course, the sequence doesn't stop here. So I can rewrite my sequence x explicitly as 2, 9, 28, 65, 126 and so on. Now if I choose m equal to say 3, then we can talk about the 3-tailed sequence x3. So to write down the 3-tailed sequence x3, we need to ignore the first 3 terms and we need to start from x4. So x4 is 65, then followed by 126. Then we will need the next term which is supposed to be x6 and that is going to be 217 and so on. So this is what we mean by the 3-tail of sequence. The m-tail of a sequence helps us to decide the convergence of the parent sequence from which it is made. So we have a short result which states that x equal to xn converges if and only if the m-tail of the sequence xn converges. And in this case, we have that the limit of sequence x is same as limit of sequence xm. So we'll be stopping for today's lecture right over here. I hope that you have understood what I have tried to convey. If there are any queries or suggestions, please feel free to put up in the comment box, and do consider subscribing my YouTube channel and also press the bell icon for more notifications. In the upcoming lecture, we will be getting in more detail and depth of sequences. Thank you so much for watching till here.